Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's enough of my face for the moment. This is a revision seminar for Maths 1A. It's Semester 1 2019. For those watching in the future, hello. And here we are. Been given some requests on the board here, and there's a lot there. Some of them are a bit vague, and I've talked to some people about what they mean by those things. I definitely can't just cover all theorems of the entire course. That's just not possible in the time that we have. But what I can do is talk about some things. So I'm going to take a vote for where to start. And all right. So all right. So I'm going to start with either matrix inverses or trig substitutions. So if you want me to talk about matrix inverses, stick your hand up. All right, I may still talk about it. And trig substitution. Yeah, I thought so. Also, the rules are that if you want to ask me anything about what I'm doing or why I've chosen to do it, or is that symbol a Z or a 2, and David, you forgot a minus sign, just interrupt me. Possibly wait till I finish a sentence, but, you know, there's only so many interruptions I can cope with, but I'm happy with most. So just interrupt me. This is for you, not me. And if I've done something that you're confused by, you guarantee someone else is as well, so please ask. Yeah, that's the rules. Okay, so trig substitution is a method of integration. And just so I can put it in context, I'm just going to think about all the methods of integration that we have in this course. So the methods of integration that we have are method 0, which is just do it, because you just know what the answer is already. That doesn't really count as a method, but that's where it is. And method 1, which is to rewrite it. This is how I organise them in my head anyway. Rewrite it, so like expand out the brackets or factorise or use a trig identity or something like that. And method number 2 is substitution. You know, plain ordinary substitution, where you notice a bit that you're going, hey, look, the derivative of that is somewhere else, so I'll just call that u and see what happens. There's integration by parts. And they're the fundamental methods of integration. And all these are the order I would generally think to try them. To say, well, first I'll see if I can just do it before I try substitution, because it's easier to just do it if you know how. And I would always try substitution before by parts, because it usually works out a little easier and there's less places for minuses to go missing. So that's how I would normally do it. And then we get into some of the more creative methods, such as trig substitution. And partial fractions. I think this is pretty much all the methods of integration you've been given in this course. I think. Pretty sure. Can't think of any ones that have names off the top of my head. And I should point out that trig substitution is a kind of substitution, and partial fractions are really just a fancy way of rewriting things. So they don't really technically count as separate methods, it's just they're complicated enough to need to be talked about separately. So if I was going to do trig substitution, the first thing I would do before doing something when if I thought something was a trig substitution, before I tried doing that, I would try these, because it might be a double bluff and you don't need trig substitution after all. So just would point that out. Okay, good. Now I've situated it in the list of things. Now we're going to do this one. So the whole point of trig substitution is to make annoying square roots go away. That's what it's for. Doesn't really matter what's there. So annoying square roots that you can't factorise away. That's the point. And the way that it gets rid of those square roots is via trig identities. Congratulations for finding the room, actually, everyone who did arrive. If you've never been here before, it's not really obvious. It's not the least obvious room in the university. The least obvious room in the university is the Mawson Lecture Theatre. You have to walk through the Rock Museum to get there. So, okay. So, sorry? Good. See, that's a good ad. Okay, so that's what it's designed for. So if you see things with roots, or even just any power that's got a half power in it, so if you've got like to the power of 3 on 2, that's got a root in it, that's what it's for. So if you see those things, that's what it's designed to do. And it tends to be quite long, because it has a lot of moving pieces to make it work. The problem with trig substitution is that even after you've done the trig substitution, it turns it into one of these where you have to rewrite it in order to do the integral. And then by the time you get to the end, there's a whole lot more rewriting to actually get the original x back when you did the substitution. So that's why it feels like a lot. So I might do one and then go back and point out the pieces. Okay. There is a list in the book of which shapes for this go with which things, and I can never remember that off the top of my head, but I can still figure out how to do a trig substitution anyway, and you might be interested in how I do that. So it has to actually be things that involve squares under the brackets here. They have to be things that are squared under the bracket for this to work. So you need squares under a root sign. Okay. And the big thing that we're going to think is that if I had a right-angled triangle, then I'm going to draw two pictures actually. If this was a squared, a, and this was b, then this would be a squared plus b squared, root of a squared plus b squared. There. And if this was c and this was b, then this would be root c squared minus b squared. This is the picture that's in our head, and it's these roots here that occur when you're doing Pythagoras' theorem that is what these trig substitutions are designed to get rid of. Okay, good. So what we actually do is we replace one of these things with sine or cos of or tan of an angle that's involved in this picture. Okay, so you would normally put an angle here. I'm going to call the angle, well, whatever. It's traditionally called theta, right? Okay, just bear with me. Sometimes it takes a while to get going if I haven't already, I don't get to prepare like your lecturer does, so takes me a moment to get going. But this is the pictures that is in my head to help me make decisions, and sometimes I won't use the pictures at all and I'll just directly use trig identities. So the other pictures that are in my head is that cos squared plus sine squared is 1, and the one that you get from here by dividing everything by cos squared, which is 1 plus tan squared, is sec squared. So these, if you just do the algebra, will also produce those same square root things. If I want to know cos, it'll be root 1 minus sine squared. And if I want to know tan, it'll be root sec squared minus 1. So these also produce those same things. Okay, cool. So does anyone have one in mind that they weren't sure how to do, or do you want me to make one up? I'll make one up. Some people have one, they went, oh, this bugged me, I couldn't do it, and so they tell me that one and I make them feel better. But I'm going to work on one that I have. Do I really want to do that one? How hard do I want to make this? Let's make it hard. because then everything else will seem easy by comparison. Okay. Bang! Let's do it. Okay, so this is a trig substitution sort of situation because it has one of these roots with squares underneath it. And so I'm thinking trig substitution is a good idea, but before I do anything else, I do want to check if ordinary substitution will help. So if I called, with ordinary substitution, you normally say that the bit that's the most annoying bit inside another function, which would be this bit here, and you would call all of that u. And if that was u, the derivative would be like minus 50x. And so if that had just been an x and not an x squared, ordinary substitution would have helped. Because I could have made my 50x into a 3x by dividing by 50 and timesing by 3, and an ordinary substitution would have been fine. So it's just worth checking if it's an ordinary substitution, even if it's got a root before you do it. But it's not that x squared. Even if I made this equal u, I'd be able to get rid of one of those x's by combining it with the dx to make a du, but there'd still be an x left over, and that would be really annoying. And so in order to deal with the fact that it's an x squared and that this root has stuff, that's what I'm going to need to do. Okay, so I know it's going to have to be a trig substitution sort of situation. And I can analyse what's written here to have a good idea of what's happening. Okay, so that is a square root with a minus. So it must be, if I was doing Pythagoras' theorem, the shorter side of a right angle triangle, because it's got the minus like this does. That way? No? Go that way. No, no. All right. So it must be the shorter side of a right angle triangle. So if I can imagine the right angle triangle that's involved, so the short side must be this, which means the long side would have to be 4, so that 4 squared is 16, and the other short side would be 5x, so that 5x all squared is 25x squared. Yay! Okay. So that's what I'm going to do. And the other thing I'm thinking would be a trig identity thing. So I'm going to do that part too, just so you can see both decision-making processes. So I know that if I had cos of something squared plus sine of something... Does your lecturer use theta instead of u? Do you feel more comfortable with a theta? Okay. I feel more comfortable with a u because I know it's a substitution, and then it makes me feel like I'm doing substitution if I use a u. Okay. But I will do what makes you comfortable. So that's the trig identity I would normally use. And I can see the shape of this here. Like that. And so it's the right shape. This 1 minus sine squared is here, only it's a 16. So if I multiply by 16, I get that. And now I'm matching, I'm doing pretty well. I've matched the minus, and I've matched the 16. So all I would need to do for this to match exactly would be for all of that to be 25x squared. So if 5x was equal to 4 sine theta, then I would get that 25x squared would be 16 sine theta squared. And so I'd end up with 16 cos theta squared is 16 minus 25x squared. And so when I do the square root, I get this. So that's one way of deciding, by purely using trig identities to try and match up from a trig identity the pieces of this root with the things that you have. That's one way. And the other way is to use this triangle. But the hard bit is deciding whether you're going to use sine or cos. So what you want to do is you want to choose your theta so that the x is on the top when you find sine or cos from this triangle. And sine is better than cos because its derivative doesn't have a minus. And we don't like minuses because they get in the way and we lose them and our answer's just wrong. So we're trying to avoid that. So if I put my theta here, then I will get sine theta is 5x over 4. And so 4 sine theta is 5x. And so 16 sine theta squared. We don't necessarily need all of this, we can just run with that. And so the x is 4/5 of sine theta. Okay, so you can choose which of these you prefer. It doesn't really matter which one. You may want to do both, just to be sure. But the whole point of this is to get to the point where this bit with the horrible square root goes away. So on this side, I deliberately tried to match up to this square root and I got to here. So now that means that this entire thing with the square root can be replaced with 4 cos theta. Over on this side, I'm going to have to do the same thing. So the sine theta is 5x on 4. The cos theta is root 16 minus 25x squared on 4. And so I have found an expression for this root now. So that's the first goal. The first goal is to get rid of the square root. Okay, and from this point forward, the working is roughly the same. Okay. Let me just go over what happened there. I saw this square root, and either I went, oh, it must be the short side because of the minus, and then I managed to find a sine theta and a cos theta to come out to what I want. Or I went, oh, okay, I can create this from the cos squared sine squared formula and get to the same thing. So let's just sum up where we are so far. So what we did is we let x be equal to 4/5 of sine theta. We don't need to let, we can probably put that anywhere. Okay, and then we use that to figure out what sine theta and what cos theta were. That was useful. So that 16 minus 25x squared is 4 cos theta. That gets rid of the annoying root, which was the whole point. But we also want to get rid of the dx. So dx on d theta is 4/5 of cos theta, because you know the number will stay there and I'll differentiate to get the cos theta. And so that means that the dx all by itself is 4/5 of cos theta d theta. Okay. Okay, so what have we got so far? We've dealt with this bit, we've dealt with this bit, we still have the 3x squared to go. So 3x squared is 3 lots of 4/5 of sine theta squared. Cool. So I think we have now found each piece of our integral has an answer to go with it in terms of theta. Let's just check. So we've got our 3x squared, that's here. We have our big root, that's here. And we have our dx, that's here. Okay, yeah, we have everything. So the 3x squared became 4/5 of yep.
Should it be 48 on 25 instead of 12 on 5? Or maybe that square?
Where are we?
Top of the second page.
There. We should totally be squaring that 4, shouldn't we? Well done. Thank you. Told you to interrupt me. So that 4 squared would be 16. And we need 3 times 16. Gotcha. Well done. Where was that? Yeah, thank you. So 48. Thank you. Squared the sign but not the number. So the 3x squared became 48 on 25 sine theta squared. And this became 4 cos theta. And the dx became 4/5 of cos theta d theta. All right. Now you may think this doesn't look much better. Well, it is better. It doesn't have the square root in it. We didn't say it would make it easy. We just said it would make it possible. Possible is easier than impossible. Though, to be fair, if you knew it was impossible, you just wouldn't do it. So, okay. So let's see if we can just simplify this a bit. That cos theta cancels with that cos theta, that 4 cancels with that 4, and we get 25, 1, right. Great. And so here we are. Now we are at a stage where we have an integral that we need to do. So let's go back to our list of ways to do integrals. Don't know how to integrate sine squared by itself. If it was just sine, I'd be good. So I can't just do it. Rewrite it. Well, trig identities are designed to rewrite things, so let's go. Well, I can't use this trig identity because that would just turn it into cos squared, and I don't know what to do with cos squared either. So I have to use a different trig identity that has sine squared in it. Okay, so I tried this one and it didn't work. What's the other one? Cos 2 theta is cos squared minus sine squared. So if I did this minus that, I would get 2 lots of sine theta squared. I made my own trig identity. Isn't that fun? Most people do that starting from the cos 2 theta, and they know a trig identity that goes cos 2 theta equals 1 minus 2 sine squared. But I like to do it from this one, because in my head the trig identities go cos squared plus sine squared is 1 and cos squared minus sine squared is cos 2 theta. I remember in that order, because then they relate to each other. Okay, and so 48 on 125, which is the integral I need to do, is 24. Brilliant. Sweet. So now I integrate that. So 24 on 125 theta, because when you integrate a plane number, you just attach the variable to it. And then this one, the 24 on 125, will still be there. The cos will go up to sine, but then because of the chain rule, I'll have to divide by 2. So when you do the chain rule with integration, you have to divide by the derivative, right? But it only works if the derivative is a constant. All right. Which would be great, except now I have to put my x's back in. damn it. Okay, so let's just go back. X was 4/5 of sine theta. So 5/4 of x is sine theta. So sine inverse, arc sine of 5/4 of x is what theta is. Right. So I can now put this theta, which is arc sine of this. That's great. Bang. Now I need to deal with the sine 2 theta. Sine 2 theta. We don't have a sine 2 theta. We've got a sine theta, we've got a cos theta. That's okay. Sine 2 theta is sine theta times cos theta. Okay. Sine 2 theta is 2 lots of sine theta cos theta. That's the other trig identity. And earlier we said that sine theta was 5/4 of x, and cos theta was root 16 minus 25x squared on 4. Okay. Sweet. So what have we got? So the integral I was hoping to do is supposed to be this. No, ignore that. I'm getting ahead of myself. So I'm just copying this line now. I just simplified it a little to get the 24 divided by 2 to get the 12. And then I'm going to sub everything in. Arc sine 5 on 4x minus 12 on 125 times 10 on 16x root 16 minus 25x squared plus c. Yay! Probably simplify that a little. Maybe. I guess the 4 from the 16 will cancel out from the 4 from the 120 from the 12. And then that'll be wow, there we go. So now we ask, what just happened? So, what did just happen? So the last thing that happened, let's go backwards. The last thing that happened was I took the answer that I was up to with theta and I subbed in all these things based on how to get x's from thetas. And those things I took from the first thing I did. So I really am going to have to start from the beginning. So from the beginning, first I decided what substitution to do, using either a triangle or a trig identity, whichever one floats your boat. And I especially wanted to make sure that I dealt with what happened with the square root. That was the most important thing. And then I picked out the bit where I said what x was, and I differentiated it to deal with the dx. And then I found all the leftover bits if there were any, and I wrote them in terms of theta so that I could finally do this. So that was all part of one piece. All of that together allowed me to turn my x's into thetas. The most important bit to happen first was to deal with that square root, because that's the point. And then I have to deal with the d theta, the dx, and then I deal with anything that's left over. Okay. Then the second part was when I actually did the integral. And the only way I was able to do that integral was to do a trig identity. So I found a trig identity that helped me to solve my problem, and then that allowed me to actually do my integral. All right? And then what I had to do is I had to take my answer and go back to my original things and find out what each piece of what I had written here was in terms of x. So the straight up theta I could get from the one that just related x and theta directly, and the sine 2 theta I had to use another trig identity and pull that out of my original working. Yep?
Can you also substitute sine theta integrate the square?
Sorry, what was that? Sine theta equals u?
Yeah.
Way back here?
Yeah. Wait,
Here? No, you could not do sine theta equals u and integrate there. And the reason you couldn't do that is because if u was sine theta, when you did the du on d theta, a cos theta would come out. And there wouldn't be a cos theta here to get rid of it. I'm just going to deliberately do that. That's a very good idea. So you're just saying, we were here, I'm so used to writing in texture in the Maths Learning Centre. You're sort of thinking if you had this with a number there, that maybe you could go u equals sine theta like that. So then du on d theta would be cos theta. And so du would be cos theta d theta. So this would be great. So this bit would become u squared. But then the only way to make a d theta is to have the only way to make a du is to have a cos theta to attach to the d theta, and there isn't a cos theta there, which is sad. And therein lies one of the things that makes trig substitution hard, because the integral you get afterwards you can't do with ordinary substitution. Because if you could do that second integral with ordinary substitution, then you could have done the original one with ordinary substitution after all, and that would have been good. So it was a really good idea, but it just doesn't work, sadly. So to get this, I had to go looking, and actually these here came from the earlier working. Or directly from the triangle. That'll work too. And then finally, basically that allows you to sub everything in and get a final answer. So there are the three main pieces, but each piece has some little details in it. That's trig substitution. So, questions or thoughts about trig substitution at this stage? I mean, a good question was, are they really going to examine this? And I can't answer that. But I can say that it probably won't be nearly as complicated as this one. Because this one I just deliberately designed to be complicated so that anything in your exam seemed easy by comparison. It is very unlikely in an exam to have one that has an x squared as well as a root at the same time. Because that forces you to need to do this sine squared thing. Because that was what, this x squared is what eventually produced this sine squared later on. So that event causes you to do that. Unless, of course, it's the only integral question in the whole exam, right? Because then it does multiple things at once. So I don't know. But the point is that after you've chosen what your substitution is, this bit in the middle is something that your lecturer expects you to be able to do, to be able to use a trig identity to turn it into something else. So we've learned two things. We've learned how to do trig identities, and we've also learned how to integrate sine squared. Okay. So let me do an easier one, one that won't take so long, just to make sure we've got all this down pat. Let's do this one. So if this had been x squared plus 9 to the 3, I could have just expanded it out. But I can't expand out roots. They don't expand out over plus. Nothing expands out over plus except times. So I can't do that. But what I can do is a trig substitution because it's designed specially to deal with roots like this. So let's see. That's a long side because it's a plus. If I put an x there and a 3 there, then x squared plus 3 squared would produce that. So really I should have written this there on the long side first and it's going to, aha, it's going to be the x and the 3, the square roots of those two things. Okay? Now, if I put the theta here, then if I do, so cos theta would be x on this and sine theta would be 3 on this and tan theta would be 3 on this. I don't want the x on the bottom when I do, all of them are more complicated than just having a single x on the top, so I should probably put the theta there. Because then I'm going to get cos is 3 on this, sine is x on this, and tan is x on 3. And that's nice because it has the x on the top. So x is 3 tan theta. Nice. And just so that we've dealt with it, we know that cos theta okay, so that's telling me how to get rid of my x squared, right? This root thing, I need to turn it into that. So that's going to give me that root x squared plus 9 is 3 on cos theta. Okay, so I've dealt with the square root part. That's the important bit. Good. I just have to deal with the dx now. Okay, so dx on d theta from here would be 3, and the derivative of tan is sec. Oh crap, it's going to turn to utter crap. I'm so sorry. This was bad, this one. Sorry. Okay. It feels easy now, but the next bit's hard. Okay. Okay, so this root becomes 3 on cos theta, and this dx becomes 3 sec theta squared d theta. Because of course 1 over cos is sec, so I've got a sec here and then 2 secs here, which means I need to be able to integrate sec theta cubed. I don't know any trig identities with sec cubed in them. This would definitely not be in an exam. I do know a trig identity with sec squared in it, but that just turns things into tan squared. and I still won't know what to do. I could do it by parts, probably. It's got a sec squared. Yeah. I'm going to commit and see what happens. Okay. So, all right, and then I will stop if it turns to utter crap. Okay. So, we can't do that. Rewriting it would mean doing a trig identity, which I don't like. Substitution, well, we just did a substitution. Substitution isn't going to help. So by parts is the go. So maybe I should have left it back there. Here we go. Ready? Okay. So by parts tend to look like this, right? You split into two pieces that are multiplied together, and then when you integrate them, you get like a something like that. Your lecturer probably uses U and V. Yeah, too late. And so one of these has a dash over here and the other one has a dash over here. That's how it goes. So I'm going to have to, whichever one has the dash here has to be integrated along the way, and I don't know how to integrate sec, so I'm going to do that way. Okay. So this is where f is 9 sec theta. So that means f dashed will be 9 sec theta tan theta. Do you know that derivative? Well, learn it now. It's a good one. The derivative of sec theta is sec theta tan theta. And g dashed was sec theta squared, and so g is tan theta, because that's the integral of sec theta squared. Okay, so we have f is 9 sec theta, g is tan theta, f dashed is 9 sec theta tan theta, g is tan theta. Oh, sure. Yeah, I think it's probably trying to stop. I can actually do this. No, the substitution isn't going to help, I don't think, because I could be wrong. No, I'd need a sec. I can't let u equals tan theta because then I need a sec squared theta on the outside, not a sec theta. Oh, look at this. Look at this. Tan squared is sec squared minus 1. Why does that help, you say? Ah, well. So we have 9 sec theta sec squared, which is where we started. And then just plus 9 sec theta. So, nothing up my sleeves. This is equal to that. So if I put this over there, I'll have two of them. Oh, I'm so happy. So not an exam question, though. Right, let's just talk about that. So, of course, I'd have to know how to integrate sec theta, which is one of the hardest integrals there is. I happen to know what the answer to that is. Yeah. The integral of sec theta is ln of sec theta plus tan theta. Just so, random things know all the words to most of the songs in the Matilda soundtrack, and I also know what the integral of sec theta is. So, if they did give this as an exam question, they would give you some hints and they would tell you what this integral was. Okay, so actually, the integral that I had is half of this, right? Because there's two of them. Okay, what did we learn from this? David is unhealthily excited by difficult integrals. Sorry? Integral of sec is pretty cool. If you want to find the integral of sec by yourself, you rewrite it as cos theta on cos squared, and then rewrite the cos squared as 1 minus sine squared, and then go u equals sine theta and sub it in, and then you have to use partial fractions to integrate that one. Yay! Okay. So, I do want to focus on this very first part. This very first part, it was not difficult. This first part was easier than the other one. The bit where I figured out how to sub in the theta was a little easier than the other one because I had a neat little Pythagoras thing going on, and I was able to figure out what the square rooty bit was, and I was able to figure out what the dx was. And so the subbing it in and getting to here was nice and short. And that's what I was trying to go for. I just didn't predict that the next bit was going to be awful. Sorry about that. However, it is possible that a person in an exam would just ask you to do just that bit, or to just show you the working that gets from here to here. It's a classic exam thing to do, to just get you to do half of something. And so I would just recommend that if you see them giving you one that you think, God, that's going to be awful, just check to see if they only wanted you to do half of it, because they're like that. They'll just get you to do a piece. And you know what? It's better to do half of it than none of it, even if they did want you to do the whole thing. And if you can do this first bit, then you will get at least some of the marks. And that's a good thing. So other things. Have you seen that trick with integration by parts where you produce the thing that you started with before? It's a neat little trick. And so whenever you're doing integration by parts, you should always be looking to see if you can find the thing that you began with, just in case it helps. And this one with sec tends to do that because it produces sec squareds, and you can turn them back into, it produces tans, and you can turn tans back into sec again. So that little trig identity here that was right at the beginning is a useful one. And I can never remember it off the top of my head. I just know that there is one that has both tan and sec in it, and I construct it from the cos squared sine squared one. Because I can never remember it's got a plus or a minus. So if I divide this one by cos squared, I get that one. So my memory is not the best for exams, but I'm good at remembering enough to figure out the things that I'm missing. And one of the things I do in my 10 minutes reading time is write down all the things that I can't remember but I can figure out. So when I did Maths 1, the first thing I wrote down was this trig identity and that trig identity from it afterwards, so that I could use them later on. And I didn't have to hold them in my head anymore. It's like my mental cheat sheet. Yeah. And there was a thing, I don't think they have it in Maths 1 anymore, I don't even remember it now, but I repeated it to myself as I walked in, and the moment I was allowed to write, I wrote it down so that I didn't have to remember it anymore. You just can't do too many of those. I think it was rotations in 3D. That was Maths 1B in the day, but they don't have that anymore. But you know, the point is, the sad thing is if you remember things by that method, you don't remember them for very long. Okay. So that's some trig identity stuff. The easiest trig identities will happen at this point. Sort of everything will cancel out and it'll just be a plain number. And they'll be the easiest ones to do. So if this had been 1 over this, then when everything would have cancelled out and I would have just gotten cos theta later on, and that would have been nice. So, yeah. All right. Well, your confidence in my ability to do integrals may be bolstered, but your confidence in me being able to make you feel better about integrals, maybe not so much. I'm sorry about that. Let's talk about something else for a bit. If you just had to yell out which of the things on that list was the most important thing for you to talk about, what would it be? I've heard of several things that say basis. What else did people say? Okay, all right. Okay. So we're now over in the algebra side of the course. Right. This thing of span and basis is the biggest idea in algebra. It keeps coming back. In fact, you used it over in calculus without even noticing. So the fundamental first thing you need to know about is linear combinations. So if you have some vectors, or indeed anything at all, you know, it doesn't matter how many of them there are, I'm just going to call them u, v and w, and you have scalars. If you calculate this, something times u plus something times v plus something times w, then the answer to that is called a linear combination of u, v and w. That's what a linear combination is, and it doesn't have to be vectors. You can take functions and do linear combinations of functions. You could take the numbers 1, 2 and 3 and do a linear combination of them if you wanted. It wouldn't be particularly important, but it's a thing that you can do. You can always multiply things by numbers and add them together and see what happens. It's called a linear combination. And it's linear because to a mathematician, linear means adding and multiplying by scalars. Okay, that's what a linear combination is. And it is the fundamental basis of... don't use the word basis, David. It's a fundamental idea that everything is built on. So the point of linear combinations is that this is exactly what vectors do. To a mathematician, a vector is a thing that does linear combinations. When we have vectors, we can add them and we can multiply them by scalars, and if we do both of those at once, it's called a linear combination. That's what vectors are to a mathematician, things that do linear combinations. That's why they're so important to us. Okay, and so we become interested in what the linear combinations do. So if we take some vectors, I'm just going to put a space here. So if we take some vectors, it doesn't matter what they are, but I'll just say that there's 3 of them. It will work with 1 or 2 or 15. So vectors, take some vectors, calculate all of these for all A, B's and C's, all right? Then what you make is called the span of those vectors. So that's what span is. Well, that's what a span is. So if you calculate all the linear combinations, every single possible, infinitely many possible linear combinations of the vectors that you have, then the object that you make by collecting them all together is the span of u, v and w. Okay, I just need to draw a diagram of this, please. And it will require me to possibly use the camera. Okay. No. Still going to happen over here, isn't it? Yep. Okay. It's me. Right. Nah. It'll do. Let's move everything out of the way. I did come prepared with some things, knowing that, do you know what, it's probably extremely likely that people want to talk about span. Okay. So, here I am in 3D space. It goes up here and it goes down there. And I'm going to draw... Ooh, that's fun. Let's do that. Yeah. That's an x-axis and a y-axis, and that there is the z-axis. Okay. So, when I make vectors, what I normally do is I take an arrow and I draw the arrow from the origin in the direction that the arrow says it goes, and then the point that I make is at the end of an arrow. And to a mathematician, a vector isn't an arrow, it's a point. It's an arrow when I want to add it to things, and it's an arrow when I want to do scalar multiplication. But when it's just sitting there, a set of coordinates is a point. So I'm going to have three vectors here. I'm going to have this vector, and this vector, and it's going to be hard to hold it, so I'm going to remove the z-axis, and this vector. Okay, here we go. So, these are my three vectors, and the points that they are really just these 3 points. There. Those are the 3 points that those vectors are. Now, so that's what they are. The span is all of the points that can be made by doing linear combinations of those 3 vectors. So I could take this one and I could go 2 of that, and that would end up here. And that's included in the span. And I could go -1 of that, and that would be here, and that's included in the span. And I could go 3 of that, and that would be here, and that's included in the span. And I could go half of that, and that would be here, and that's included in the span. And in fact, every possible multiple of this vector would be included in the span. And so all of these points are part of the span of that vector. But then I also have to include anything that's made out of 2 of these. So I could have 1 of this one and 1 of that one, and that would produce this point. And I could have 1 of this one and -1 of that one, and that would produce this point. And I could have sort of -2 of this one and 3 of this one, which would be that point. And if I do all the combinations of the 2 vectors, I will produce all of this, right? That's what spanning is for 2 vectors. If I want to do all of the vectors that I can possibly produce by doing all the combinations of these two, I will produce an entire plane forever. Like I could get 257 of this and 762 of that, and it'd be like over there somewhere. Yeah, it's more this way than that way. So like right over there. So I can produce anything I want. But now if I have the third one, I could go 1 of this one and 2 of this one, 2 of this one and 7 of this one, maybe only 2 of them, and that would be here. Or I could go, 2 of this one and 4 of this one and minus 6 of this one, which would be like down here. And I could, if I wanted to do all combinations of those 3 vectors, I could produce every point in space. That's what spanning is. The thing that I make is everything. Right. This is one of the reasons there's a graph on the floor in the Maths Learning Centre for doing that sort of thing. You come and sit with me on the mat, please, like you did when you were in kindergarten. Some people get annoyed and they say, oh, you've got a maths kindy there. And I said, yes, kindy is awesome. It was the best year of your formal education. University should be more like kindy. Okay, so that's what span is. So when I whack span onto these vectors, it turns these 3 vectors into the entire of space. If those 3 vectors, if instead of those 3 vectors, I had these 3 vectors, then I would actually not make the whole of space. I would make, well, if I just had those 2, just those 2 made all of this, and if I had a third vector that was on the table, I couldn't make anything that I already hadn't made. And so sometimes when you span 3 vectors, you just get a plane and not the entire of space. So this is like a line or a plane or the whole of 3D space. That's what this thing tends to turn out to be. So when you whack span on some vectors, you produce an object made of a whole lot of points. Right. So we started with vectors, which were arrows and points, and we found ways of doing linear combinations. And when we did all the linear combinations, it turns points into spaces, into planes and lines and stuff. That's really interesting, because if I'm in a plane and I combine things that are in the plane, I can't make anything that's not in the plane. This blue one here and the green one and the yellow one, they're inside this plane, therefore they can only make more vectors that are inside this plane. It's impossible to escape this plane by doing linear combinations of things that are in the plane. So the plane is self-contained with respect to linear combinations. And that is what a subspace is. A subspace is a set of points that can't be escaped by doing linear combinations. It's self-contained when you do linear combinations. You can't get out. If you do addition or scalar multiplication and any combination of those, you can't get out of it by just doing those operations. And why do we call it a subspace? Well, mathematicians use sub for a lot of things. So it's a space. A subspace, a sub-anything, is a smaller part that behaves like the whole thing. So if I'm in all of R3 and I've got my 3-dimensional coordinates, I can do whatever operations I want on them and I'll only be able to make more things with 3 coordinates. And I had them already. So 3D space is self-contained. But a plane in 3D space that passes through the origin is also self-contained. And so it behaves like 3D space does, but it's smaller. And that's what sub means. The real numbers are what they call a subfield of the complex numbers. You can't get out of the real numbers by just doing things with real numbers. The only way to get out is to do by just doing multiplication and addition. You can't get out of the real numbers that way. If you want to produce a complex number, you have to do a square root at some point. So same deal. That's what's called sub. Okay, so it's self-contained by linear combinations. That's what sort of the idea is, but the definition, it just uses the addition and the scalar multiplication separately. So there's an actual definition. Set of vectors V so that the 0 vector is in V if U and V are in V. No. If U is in V and a number is a real number, then when you do scalar multiplication, it's still in V. And if U and V are both in V, then when you do the addition, you can't get out either. But these together say that if you do a linear combination of things, you can't get out. If I start with U and I multiply it by something, it's still in V. If I start with U, these in V, and I add them, it's still in V. The reason I put them in this order, which is probably not the order that your lecturer puts them in, is that this one uses one vector and this one uses two vectors. So it just makes sense to me to have them in that order. So you only need one vector to break this one, but you need two vectors to break this one. So it's easier to check them in this order. So that's the definition of a subspace. And anything that does that is a subspace. So we've already seen that if you have a line that goes through the origin, it's definitely going to be a subspace because you can't escape it by doing multiples. And if you have a plane that goes to the origin, you can't escape it by doing linear combinations, so it's a subspace as well. And the whole of R3, you can't escape it anyway, so it's a subspace of itself. That's the idea. But it all comes from linear combinations ultimately. So here's the question. What if someone gave you something that was a subspace but didn't tell you how they made it from spanning stuff? So we just saw that one way to make a subspace was to span something. If you span two vectors, you make a plane, and a plane is a subspace. If you span three vectors, you make everything a subspace. What if you were given the final result of a span and wanted to know what things spanned it? That's a good question. That's what a basis is. So if you have a subspace already laid out for you, if you have a subspace and you ask, let's call it V. V is the span of what? All right, that's the question. What goes here so that you can create V as the span of something? The answer to that question, that's a basis for V. So if our question is V is the span of what, the answer is a basis for V. That's what a basis is. Now, that's not quite good enough to be a basis because just like my plane on the table here, I don't actually need all three of those arrows to make the plane. I only need two of them. So a basis is the smallest list of things that you can put in that spot and produce the subspace. If it's the shortest possible list. Now that's not the definition, that's just the idea. The idea is that I might, in space I might draw a plane and say to myself, cool, what vectors span this plane? And I'll go back to here and go, here's a plane, and there's the origin there. I could choose this vector and this vector. Let's draw them. I could choose those two vectors, and together they would be able to make the whole of this plane. So they are a basis for this plane. One vector wouldn't be enough. That would only make a line. I definitely need two. And three vectors would be too many, because if I have a third vector, I can make it out of the other two. So two vectors is the right number to be a plane. That's the idea of a basis. So it has a definition as well, because we wouldn't be mathematicians unless we had definitions. Yep. A basis can be one vector if you had a basis for a line. Yep. That is an excellent question. You should always ask questions about the edges of things. It couldn't be a basis for R3, but it could be a basis for a line inside R3. Yep. So I might just articulate that first. So just the span of this. So that, for example, the span of 107, that would be a line in R3. And so I could say that 107 is a basis for the line. The basis belongs to the line. But you're right, it's totally not a basis for the whole of R3. It's just a basis for that bit. So that might be, your lecturer did start off talking about a basis for the whole of R3, but every object inside R3 has a basis of its own. Yeah. Okay, that's a line. This is a basis for that line, but it's not a basis for the whole of R3 because it doesn't make the whole of R3, it only makes the line. Yeah. It's a little bit like saying that a basis for my name would be the letters D and A and V and I, but they're not a basis for the whole of all possible names, just my name. That's the idea. Yep. Okay. Cool. So we need a definition of basis. So a basis for subspace V is a set of vectors in V, and it has two rules. One, it has to span V. So you might have noticed a little switch there. Span, when I originally defined it, was a noun, it was an object, but now I'm using it as an action. Yes?
The bases are only defined for subspace.
Yep. And so since R3 is technically a subspace of R3, it's the biggest subspace. R3 has a basis of its own. Actually has infinitely many. You can choose any three vectors that are pointing in different directions and it'll make a basis for R3. Yes, but it is a very important point that a basis is not a thing all by itself. It's a piece of information about a subspace. Yeah, you can't just look at something and say, is that a basis? You go, well, is it a basis for what? Yeah. Because you just like saying, look at this thing, is that a beginning? Well, is it a beginning of what? That's the idea. Is linearly independent. Yep.
The vector 107 the basis of the line. That would only be true if the line went to the origin, right?
Yes. So when I do span, I automatically include the origin because 0 times something is a perfectly good linear combination. So that's why subspaces always have to include the origin, because you're always allowed to include the combination of 0 times u plus 0 times v plus 0 times w. These are very good questions. Okay, so that's the definition of basis. This bit is what I was saying, and you know I have to go v is the span of what, and that's what a basis is. And this bit guarantees that it's the shortest list I could possibly come up with. But that means I need to have a definition of what linearly independent means. So the idea of linearly independent, well, I should put basis. The idea of linearly independent is that none of them is already a combination of any of the others. Because if one of them is already a linear combination of some of the others, then I wouldn't need it because I can make it out of the other ones. So none of them is a linear combination of any of the others. That's the idea of linearly independent, but the definition is a little bit different. And the reason the definition is different is because it's easier to check. The definition is that there is only one way to make the origin as a linear combination of your vectors. So definition, v1 up to vn. I put underlines under my vectors to tell you that they're vectors as opposed to numbers, just so you know. In a printed text, they would be in bold. So are linearly independent. All of the vowels in independent except the I are all E's. Don't put any A's in there. V1 up to Vn are linearly independent when the equation x1 v1 plus up to xn vn equals 0. That's the 0 vector, by the way, the vector all of whose coordinates are 0. It's not the number 0. That's why it's got an underline, because it's in bold, because it's a vector. Has only the solution x1 equals 0 all the way up to xn equals 0. That's the definition of linearly independent. So what this says is that if I have a linear combination of these and it comes out to be 0, the only possible way to do that is to have 0 of all of my vectors. That's the definition. So the reason why these vectors were not linearly independent is because I can make this one out of those two. If I go, give me a second, it's because I can arrange enough of these so that it's equal to 0. Let's see. I could have, yep. Ta-da! This plus this plus this is 0. So I was able to create 0 without using 0 of each of them, and so they're not linearly independent. Yeah. That worked out well. Okay. All right, it doesn't have to be plus. It could have been 1 of this and 2 of this and minus 7 of this comes out to 0. That's the definition of linearly independent. So those ones were linearly dependent because I could make 0 out of the 3 of them without and have actually them there on the page rather than just not having anything. And also that means that any one of them has to be a combination of the other 2. That's the definition of linearly independent. And we use it because it's really easy to check this if I know about how vectors and matrices go together. So solving this equation is the same as row reducing a matrix with the vectors as columns. And so that's why this is a definition, because it's easiest to do. It's also this, because it's actually easier to do than this. To check that none of them is a linear combination of any of the others would take a lot of work because you'd have to do each of them separately. Whereas this allows you to do them all simultaneously in one go. Yeah. So, it's probably productive at this point to like pick a question that uses these information and try and do something with it. Yeah? All right. I'm just going to have a quick look in the notes. Yeah, I may have gotten ahead of myself and done some Maths 1B things there, but that's okay. But that's all right. I think that the concept of basis doesn't make any sense unless you do it for all subspaces simultaneously. So the idea of having a single subspace having a basis of its own is part of Maths 1B. I'm sorry, I got a little bit ahead of myself there. So they won't assess that in Maths 1A. But it's a useful idea that everything has a basis of its own. So here's a question. Is that a basis for R3? What do you think? Yes? Why? That's a good guess. Well, I'm not going to. Guessing is fine, but we want to know how to get it. Yep. Only makes a plane, you say. How can you tell? There's only two of them. I'm not going to be able to make all of the vectors in R3 because I definitely need 3 vectors to make everything in R3. So they're definitely linearly independent because this one is not a linear combination of that one. So they're definitely linearly independent, but they are not, they do not span. So a really good, I can tell you a vector that isn't in the span of those two, and it would be just a second, give me a second. Don't write this down yet. 138 is definitely part of the span here, because there's this one plus this one. That's definitely in the span. That one won't be, because I only changed one coordinate. If I'm going to change coordinates, I have to change either them in the pattern 1, 2, 3 or in the pattern 0, 1, 5. Is not in the span of 1, 2, 3, 0, 1, 5. So no. But on the other hand, you are actually allowed to say that R3 needs 3 vectors for a basis, so it can't be a basis for R3. In Maths 1B, they define that as dimension. And dimension is the number of basis vectors you need, and R3 is definitely 3-dimensional, and so it needs 3 basis vectors. A plane is 2-dimensional, so it needs 2 basis vectors. Okay. Is that a basis for R3? So 1, 2, 3, 4, 5, 6, 7, 7, 8, 9. Certainly got the right number of vectors. Has someone seen something? So can some people tell me what they're trying to do? Yep. See if they're really independent, and how are you trying to see that? Seeing if one's a combination of the other two. Cool. So if you just wanted to, that is an excellent approach, and actually one of them is a linear combination of the other two. This one is half of that plus half of that. So yeah, this plus this is 8, 10, 12. And so you divide by 2 to get that one. But if you wanted to give up and not look to see if that was possible, the best way to tell is to see if they're linearly independent by putting them as columns in a matrix. So you could do this. Technically there's a 0, 0, 0 here, because what you're trying to see is if x1 times this vector plus x2 times this vector plus x3 times this vector is equal to 0, and seeing if there's more than one solution for that. And so you could row reduce and see what you get. So row 2 minus 2 of row 1. And row 3 is row 3 minus 3 of row 1. And now I could do that. And now if I did row 3 is row 3 minus row 2, I'll get a row of zeros, which means a row of zeros is going to prevent there being a pivot in every column, which means I'm going to get a free variable, and at least one of the x's is allowed to be whatever I want, including not 0. And so that breaks the definition of linearly independent. Yeah. x3 is anything, i.e. x3 does not have to be 0. And the definition of linearly independent was that when you did x1 times vector 1 plus x2 times vector 2 plus x3 times vector 3, and they came out to 0, the only way to do that was for all of the variables to be 0. And I've found that the x3 doesn't have to be 0, so they're not linearly independent. Now you are allowed to just do that. The moment that you prevent there being a pivot in every column, then they can't be linearly independent. And the moment you get a row of zeros, you prevent it from spanning. So they also don't span. So if there's the right number of vectors to be a basis, and they don't span, then they can't be independent either. Yes?
Can you give an example for spanning subspaces, whether someone spans a subspace and improves on it?
Yep. I have a feeling that's not in this course, and it's in Maths 1B. But is it? Have we done basis for a subspace? Sorry? We have? Okay, all right. Sure. Just give me a second. So you want to find a basis for a subspace?
No, more like prove something, like prove some scans
Spans a particular subspace.
Yeah, and word of line.
Okay, so something like this. That sort of thing? Okay, I'm going to use this same subspace and ask several questions, okay? So this is a subspace. I know it's a subspace because it's a plane and it goes through the origin. And anything that's a plane through the origin is definitely a subspace. So, and being a plane, I expect it to have two vectors in its basis because all planes do that. You haven't proved that in Maths 1A, that's in Maths 1B, but we'll be fine. So do they span V? So that means that they need to be linearly independent. Do they span V? I could ask if they're a basis for V as well, but let's ask if they span V. Well, the first question is, in order to span V, they would have to be in V. So let's see, 1 plus 2 minus 3 is 0. That vector's in V. And 0 plus 8 minus 7 is 1, which is not 0. So 0, 8, 7 is not even in V. So no, they don't span V. So that's the first secret rule 0, which is they have to actually be in there if they're going to span it. So I like to use that one first. So what about 1, 2, 3, 17, 38, 51? Do they span V? Well, let's just check if they're in there. Let's see, 0. So 17 plus 38 minus 51 is indeed 0. No, it's not. Sure. Damn it, I really wanted it to be in there. 2 times 17 is 38, isn't it? 34, yes. You can tell I've done 2 revision seminars today, or just my mental arithmetic's pretty bad most of the time. That's the one I want. Right, yes. Okay. So they're definitely in V. If they were going to span V, I'd need them to be at least 2 of them. Well, they don't span V because this one's a multiple of that one, and they only span whatever 1, 2, 3 spans by itself. And you can't span a whole plane with only one vector. So the span of 1, 2, 3 and 17, 34, 51 is the same thing as the span of just 1, 2, 3. Because I don't need this one. Anything that I could span with both of them, I could span with just one of them, because this one's already a multiple of that one. And so that's never going to span a plane, it's only going to span a line. Okay. I don't know if there's any good methods other than this. This is just the only thing I can think of. All right. Well, the only other way of me knowing for sure that they span would be that if they were linearly independent and they were both in there, they would have to span something, and they would have to span a plane, and since it is a plane, they would have to span the whole plane. That's the only way I can think to do it. I wish there was something better than that. Yeah. Do they span V? Well, they're definitely both in V. And since they're independent, whatever it is that they do span is a plane. So, the only other way to be sure, yeah, so this is an argument that I would give, you know. I know they're independent because this one's not a multiple of, well, that one's not a multiple of that one. Because if it was, there'd be a 0 in this spot. And with two vectors, you just have to check if they're not multiples of each other for them to be independent. With three, you have to do the matrix thing or just guess. Okay, so these are linearly independent. They span a plane because there's two of them. Well, the only plane they can span is the plane that they're in, and so they must span V. This plane has to be in V because it's made of vectors that are in V, and so it is V. Therefore, they span V. I'm not sure if they would like that argument, but it's the first one I thought of. I love that sort of argument. They will have to span something, and it's not a line, so it must be a plane. It's not a line, it's not the whole of R3, so it must be a plane that they span. And anything that they span has to be inside V, and so they span a plane that's in V. V is a plane, so they have to span V. But I don't say that much words on the page. Okay. So the only other way I could check if two things span V would be for them to happen to work out to be a basis for V when I found the basis for V directly. So let me just see what happens when I attempt to find a basis for V. So if I want to find a basis for V, I need to find a couple of linearly independent vectors that span it. And that little argument about, well, they have to span something, so it must be V, just sounds a little bit wishy-washy, so I'm just going to directly find a basis. So if the point x, y, z is in V, then x plus y minus z is equal to 0, because that's what it means to be in V. That's a minus, not a plus. So z would have to be equal to x plus y, and so x, y and z would be x, y and x plus y, which would be x lots of 1, 0, 1 and y lots of 0, 1, 1. Very creative there. We have 1x, no x is 1x, that's how I made this, and no y is 1y, 1y, that's how I made this. So every vector that's in V is a linear combination of these two vectors. That's the definition of what it means to span. To span means that everything here is a combination of something. So that's saying so they span V. And they're linearly independent. And so therefore 1, 0, 1 and 0, 1, 1 is a basis for V. Planes in R3 are very nice. You can find a basis that way very quickly. Just write one of the variables in terms of the others and separate it out like this and it just happens. Yep? Yes, that's basically what I did. I just have a system of one linear equation with two free variables, which are x and y. So if I had had two equations, then I would have used row operations to solve it, and that would have given me, yeah. So when you are solving row operations of a matrix equals 0, you're finding a basis for a subspace. That's what you're doing, which is really cool. All right. Oops, sorry. Not quite enough space to fit a whole A4 sheet on. I just can't get this any further away from the table. Also, I write huge, so I always need extra paper in my exams. Okay. Wow. So are there any other kinds of questions that you were asked around this topic that you're not sure how to tackle, that you want to talk about? That's all good. I will say one thing, because it's probably, I just want to say it because it's one, I love it so much. It's not important, but I love it. I love it a lot. I'm not going to actually do partial fractions. I just want to tell you something. So if you had something that was like this, if you had something that was like this, and you wanted to split it up into its pieces, if you don't split it up into the right number of pieces, it won't work. Like this partial fractions process is designed to split a fraction up into various different bits. And if you don't have the right number of bits, it's not guaranteed to work. And the reason it works is because of subspaces. It's so cool! But just, yeah. So look at this. If I think about all of the things that could have been here, so if I think of all the things that this could have been, this process is designed for things where the numerator has a lower degree than the denominator. The denominator has degree 4, and so the numerator could be up to degree 3. So this thing could have been anything that's like a plus bx plus cx squared plus dx cubed. Okay? So those things, these things, require 4 letters to tell you what they are. A and B and C and D. That makes them 4-dimensional. There's 4 coordinates, A, B, C and D. So if I want to write this as a combination of other things, I'm going to have 4 of them, or I won't be able to make all the possibilities. So I need 4 things to add together if I want to produce this, all possible answers here. So at the moment, And that's why you need 4 things. You'll have some number of this, and some number of this, and some number of this, and some number of this. Look, it's a linear combination. Some number of this thing, some number of this thing, some number of this thing, some number of this thing. We used to do that to vectors. But now we're doing it to functions. And so because this needs 4, no matter what way I'm going to write this, I'm going to need 4. So I pick 4 functions that can be written to have this denominator. And that's why I need 4. It's a basis thing. This thing is 4-dimensional. It needs 4 vectors in its basis. I think that's the most fabulous thing in the world. Yeah, there you go. And these 4 functions are linearly independent. Right, that's enough. Don't forget the Maths Learning Centre is open until the end of the exam period, 10 a.m. to 4 p.m. Monday to Friday. And then you would go, okay, I'm able to get people in every row, and so therefore they spend 90. But there will be people here eventually.
Oh yeah, we need, yeah, that makes sense.
So,
and then just one more thing, that when you split up the fractions in that last one, you had C over whatever, and then you had dx. I'm just confused why. Like, wouldn't you split that up and then do it?
this one doesn't factorize.
Doesn't? Okay. So is that what you do when it doesn't factorize? Yeah. Okay.
So if it doesn't factorize, you're not going to be able to do this. And so you're going to have, if it doesn't factorize, you need 4. I'm going to need 4 because there's 4 options here, so I need 4 here as well. So I make an extra one that has an extra selection.
Yep. And then you just thank you.
So what was the logic for like how you come up with that 4 point?
Well, definitely, if I have this, it's not going to cover all possibilities because there's only 3. So I definitely need a 4th one. And I definitely need a 4th one who I can write with this denominator if I want to. Yeah. So I know that this I can write with that denominator, and if I put it over a common denominator with this, it will only have an x cubed. Like if I multiply by the x plus 1 squared, I'll get an x cubed on the top. So it's fine, it still produces something with up to x cubed on the top. And so that's the reasoning behind it. So at the moment, if I put this over a common denominator with this, I only get an x squared on the top. And so I actually haven't overall covered anything that produces an x cubed.
So you
And so this one will produce the x cubes.
Okay.
Yeah. So basically, if you can't make them, this one is not a multiple of that one, not a number multiple of that one. And this one isn't a number multiple of that one either, and so they're independent. So
we did them in the form of like dx plus
dx
c.
plus c, yeah.
And you just broke it up.
But in my head, it's vectors, and so it makes more sense to me to have.
Oh, okay, yeah. Because they don't dx plus c. Okay,
Yeah.
that makes sense. Yeah.
But I also know that if you're going to integrate this, you're going to have to separate the c and the dx anyway. So I just do it right with you.
Okay, yeah.
Yeah. And in fact, the thing that you should do is this.
Change it into the derivative of the bottom one.
Yeah.
Because then you've got the nice substitution.
Oh,
no, that's the, that's it. It is, actually, there's a really useful one that I think it's probably in the notes somewhere, but I had to point it
What
out.
happened in the Maple TA, they got you to do this.
Yeah, if ever you got f dash x on f of x, then it's just ln of fx plus the x, of course. Is it ln of fx or
ln of f of x.
f of x?
Of the absolute value of f of x.
It's just that.
Yeah,
If you've got the derivative of a function on a function.
Yeah.
If you do substitution, you'll get u equals that, and then the f dash x will come out and you do the derivative.
Yeah.
And so this is a shortcut for doing substitution.
Yeah.
Same as this one, right? That's a shortcut for doing substitution. If I did u equals 2x, then my dx would be half of du, and so I end up with a half coming out. But you're allowed to just do this. Yeah, you're only allowed to divide by the derivative if it's a constant.
Yeah.
So when you do chain rule, you multiply by the derivative inside. When you do integration, you divide by the derivative inside. But you're only really allowed to do that if it's a constant or if it's already there.
Okay.
Yeah, which causes problems. And so that's why we have problems with those trig substitutions, because the derivative of the thing inside the root is 2x. And when you divide by that, there's still an x left over, and then there's nothing you can do about that. So you have to find a different way of dealing with it. Yeah. So yes, this is why I know I could do x if I wanted, but I just need to choose something that isn't just one, like that isn't just a constant. And so I will choose to use the derivative at the bottom, and then it'll be easy to integrate when I get there. If you were doing partial fractions for a different purpose, because there are other purposes of doing it, then you would make different choices about what to put here.
The choice of putting that there is going to affect what the other top.
Yeah, it's going to affect what this d is.
Oh yeah. Will it affect the A and B?
Yeah, it won't affect the a and the b, but it will affect both the d and the c.
Okay.
Because I do have a constant over x squared plus 2x plus 5 here, and so the d will be half of what it used to be, and the c will be what it used to be, but minus 2 or whatever d works out to be.
Yeah.
But I don't care. I just care of turning it into something that will work.
Okay.
And actually, this one I should probably put a fifth there. Maybe not a fifth, a half there. Because the only way to integrate this would be to complete the square and do a 2.5 10. So, yeah. Yeah. But yeah, the reason that I need 4 is because there's 4 coefficients that could go at the top here. And I like that. I don't necessarily even care about the subspace thing. Just like to know that they have to be the same number. Yeah. Cool. Well, anything you want to ask while we're here before you run out?
Other questions?
Yeah.
You guys?
That answer for the big nasty trig substitution.
Yeah.
Did you leave that in terms of theta at the end?
Oh, I may
I
have.
thought you did, which was a bit confusing because it feels like you've not actually answered it. You're like, oh, look, you've done it. I know what the derivative of this is.
Oh, I did.
Well, this is, so it's
Yeah, I
not,
didn't finish that.
it's not actually done.
It's not actually done yet. Oh well, here we go. Just a second. I'm going to finish it. Let's see.
Just have to substitute it straight into it, don't you?
Just.
Just.
Okay, so I know what tan theta is. It's x on 3, so I can sub that in. Sec theta, I guess I can get from here. Sec theta would be 1 over this. Good. Okay, so I can do that. So sec theta, according to this, would be root x squared plus 9 on 3. Tan theta is x on 3. Right. There we go. And look, these 3's cancel with that 9. That's kind of pleasant. These ones don't because they're trapped inside the element. So, in fact, they would end up being like a... No, don't want to do it. Well, no, they just end up part of the plus c, wouldn't they?
Yeah.
Because it's multiplied by ln of a third. And so when multiplication inside ln is addition on the outside,
So it's constant.
and so you end up with 9 on 2 ln of stuff plus 9 on 2 ln of a third. And that's just a constant, so I can subsume it into the plus c. Oh, wow.
So it would come out almost nicely.
Yeah, no, not really. Yeah. So yeah, this integral, if you look up a book, like a textbook, it will be there, because it's not something that's easy to do by hand.
Yeah, I remember that was one of the ones that you have like the common ones you go, ooh, easy, easy, easy.
Yeah.
Let's not, and then
It's not even here, is it? Yeah, they don't even list
Is
it.
that with James Stewart changes?
That's version
Really?
6.
Ah,
I think we're up to 8 now.
how much do they change each edition of a textbook?
Not much. Much changed.
Just enough to make you buy them.
Textbook. I'm actually happy to go to this for you on recording. Textbook companies are a bit of a racket. That's a lot of money that they spend, that people spend on them.
You would have thought.
There it is. Number 14 on this list.
I'm not going to remember.
So
No, you don't
just
have
gotta
to.
memorize that one.
If they want you to use it, they will tell you that. It's not an easy to integral to prove that that's the answer. And if you go and look up proofs for that being the answer, it's sort of based on knowing that that's the answer, which doesn't really, it's not that inspiring. So, good pointing out. It's too late now. I can put a note when it goes on there to say it's at the end.
So I don't know, I don't think anyone will miss it.
Everyone's like, what?
They're like, yeah, we're doing this.
It's worth noting that the lecturer, they try very hard to make things not too difficult in the exam.
Just test the concept.
Yeah.
Is it true that it's the examinable material have to be covered in the lectures?
No.
No, it
So
says it on
can
something. It says
examinable-
anything in the assignments, tutorials,
Yeah.
notes, or lectures.
And so, for example, this thing,
Probably won't get me.
Yes.
this partial fractions thing where you have that derivative on the top, the only place in the course that is in one of the Maple TA questions.
Oh, really? That seems
I swear it was one of the assignments.
Well, the only place someone explicitly told you that that's a thing that you could do. One of the Maple TAs kept asking you to find the J and the K and the L and
Yeah.
whatever, and it was this.
It's painful.
And no one even noticed that was going on because there was just so much crap happening in
Yeah.
that Maple TA question. But
it was like they were making us take a really long round.
They were.
Yeah.
That was on the last page.
Yeah.
yeah, whereas if you had done this directly, you wouldn't have had to go through that road.
Yeah.
Yeah. So, anyway.
Actually, with that question, isn't that in the form? Now you go yeah, isn't that basically just in the form dx plus c again?
It is.
So why not just do it when it was in the original one? Or can you, because
Because-
dx and c will be
Because
something
if
else.
I had the dx plus c,
Yeah.
I would have had to have this as an x, because I have this one here as well. I would have had to have this as an x, and I would have had to do a substitution. Let me show
It
you.
might not be the right dx and c for that derivative, would it?
No,
Okay. I see.
not the ones you want. So if I had gotten to here, if I had gotten to, was it 5?
Yeah.
So suppose I did this bit by substitution, right?
Mm-hmm.
I don't have a 2x plus 2 dx.
I see.
The only way for me to deal with this
Is to create one.
is to create a minus 2 here. So, because I pulled a d out the front, right? I have an x dx,
Mm-hmm.
so I could times by 2, but I'd have to put like a plus 2 and a minus 2,
Mm-hmm.
and then that minus 2 thing would end up over here as part of the c.
Yeah, I see.
And so it would all just become awful.
Yeah.
Yeah.
I think that's it.
Yeah.
Yeah.
Thank you so much.